Welcome to this new video on field effect transistors. So in the previous videos on this unit, that is field effect transistor, we had seen the basics of field effect transistors, how they differ from usual VJT. We have also seen the construction and working of JFET, junction field effect transistor, with its output drain characteristic as well as transfer characteristic. There are other type of FETs also. So we will see uh, in this particular video specifically enhancement type metal oxide semiconductor FET. Okay. So let's start with that. Yeah. So first thing is, so there are metal oxide semiconductor field effect transistor. They are mainly of two types. One is enhancement type and other is that is depletion type. Okay, even enhancement type, that is again divided in two parts, that is n channel or it is called E-MOSFET, n channel E-MOSFET, and p channel enhancement mode MOSFET. Okay, similarly the depletion type, which is also called D MOSFET, it is also divided in two parts, that is n channel and p channel D MOSFETs. Okay. See why the name MOSFET, the common name here, that is MOSFET, metal oxide semiconductor. So as the name suggests, first thing is this is a type of FET, that is it's a field effect transistor. So that means the electron, that is the current or the electron density, that is going to be controlled by the external electric field. Okay, so that's why that is called field effect transistor. So that is a common characteristic whether JFET or MOSFET. Okay, so first thing is they are FATs. Second thing is it says it is metal oxide semiconductor. Okay, it is specifically about the junction phenomena, that is actually the construction has a capacitor like arrangement, capacitor like structure. Okay, the metallic plate that is made up of, that is one side that is made up of metallic plate. Okay, and another side made up of semiconductor material, and in between there is a layer of oxide material which acts as an insulator. So that's how this works as a capacitor. Okay, so the common in all these types of field effect transistor is there is a MOS type, that is a metal oxide semiconductor type of capacitive construction is there. So that is again one more common thing, and why they are called MOSFET. Okay, we will see in detail what is this. Okay. So first let us see the enhancement type MOSFET, that is E-MOSFET. Specifically we will see the construction of an N-channel E-MOSFET. N-channel E-MOSFET. So if it is N channel, first we take a substrate of P type material. Substrate, or you can say it is the base of P type material. Okay. The doping level is kept low here. That is, it's a P type. So that is whatever the donor impurity concentration, that is quite low. Okay. So doping level is low here. Now on it there are developed these two regions. These are the two regions, that is with very high N type of doping. So that is high doping, that is represented by N plus. Okay, N plus indicates it is highly doped N region. Okay. Now on this there are contacts developed. So that is one side, that is on side, this is metallic contact, that is say source. On the other side there is a metallic contact is developed, and that is called D, that is drain. And on the substrate also there is a metallic contact developed, and that is called substrate SS, the symbolically to differ it from the source. So it is substrate SS or the base B. Okay, so this way metallic contacts are developed. Okay. So you will be surprised, that is where is the gate terminal and how it is developed, and there comes the actual definition of MOSFET. Okay, so let's see in the next slide. Yeah, so here what we do actually, that is yeah, here there are two things have been shown. That is, first thing is that near the N plus region, both the sides, because there is N plus and P, there is going to develop a barrier. This is the depletion region developed. Okay, when no biasing is given, the width should be same everywhere. Okay, because we said the doping level is in this region is same everywhere. So as the doping is same, the junction width will be same everywhere. Okay, one more thing is the gate terminal is developed. How it is developed? So first, near the substrate there is developed this region, that is SiO2. SiO2 region layer is developed. It's a very thin layer of silicon oxide. Okay, so the length of this, that is the actually you can say the depth of it, that will be kept of the order of 1000 to 10,000, 1000 to 2000 angstroms. Okay, angstrom, you know, that is 10 into 10 to the power minus 10 of meter. So that is angstrom. Okay, so it will be of this order. Okay, that means it is a very thin layer of oxide. Okay, and on it there is a metallic contact developed. Okay, that is we call this as a gate. We know it's a common phenomena, that is whenever we have to construct a, that is a contact. So for that, metallic contacts are developed. Okay, and this is a everywhere common. Okay, so just here the metallic contact are shown in one way, and the junctions are, that is in the metallic contacts are shown as hash lines, and the junctions they are shown dotted. Yeah, so metallic oxide, that is a silicon oxide, that layer that works as actually insulator. Okay, let us see now working how the channel, where is the channel actually. So how the channel is constructed, and basically it is enhancement type MOSFET. So there is no specifically prepared pre-prepared channel is there. It is going to get enhanced. Okay, based on the biasing. Okay, so working and operation of N-channel E-MOSFET. Okay. Now, the gate terminal is made positive. That is, gate terminal is made positive compared to the source terminal. And before that, one more thing, that is the source terminal, that is actually shorted with the substrate terminal. Source is shorted with the substrate terminal, and that has to be grounded. Okay. So actually this shorting, that is source to substrate sorting, that is internal. Okay, that's why you can see many times, that is instead of four terminals of a FET or MOSFET, there will be shown only three terminal, because source and SS terminal, they are shorted internally. Okay, and externally the source is grounded. Okay, source is grounded and gate is made more positive. This gate terminal is made more positive than the source terminal. Fine. So now what happens? What is the phenomena that will happen? Okay, there will be two types of phenomena simultaneously. There are going to be two phenomena. Okay, so there are two phenomena simultaneously will happen. First thing is, what will happen, as we said, this is a metallic contact, on other side that is a p-type substrate. Okay, that is a semiconductor material. In between there is an oxide layer. Okay, oxide layer is there. Fine. So this two works as a plates of capacitor. This two, that is metallic contact and the semiconductor on this side, they work as two plates, and in between there is an insulator made up of SiO2 material. Right? This is working as a that is insulating material between capacitor. And the working of capacitor, we know what happens if you connect one plate to be plus, that is at the positive terminal, there will be induced equal amount of voltage on the other terminal. See, there is a internally what happens, you may not be exactly aware of how the working of capacitor is, but what happens is, because of the positive terminal, there are electrons going to be attracted, that is they will be concentrated on the positive terminal, but the equal amount of because say there is external field that is available, that is across the wheel this way, across this layer. So that will be in this direction, external field is developed. So because of this external field, now what happens is actually see, there are no free electrons that can move, so there is no direct connection, but there are atoms, or actually there are electrons which are in the final orbit, valence orbit of the insulating material, which can still slightly move by their positions, and this slight movement, that is slight displacement, that is how it is called the storage of charge. And whenever the external charge is removed, okay, that will be, they will come back to their original position, and this is how the capacitor is actually storing the charge. Okay, anyway, you may not exactly be aware of means you can try to understand the working of capacitor somewhere else. That is once again I will say in short, that is basically there are insulating materials, so there are no conductors. So whenever external field is applied, what happens, there are no free electrons which will be moved, but there are electrons which are in the valence band. Though they cannot be free, they can slightly shift by their position. Actually they get oriented towards the externally applied electric field, they get oriented towards this, and this is the displacement, this is a minor displacement within the orbit itself. Okay, within the orbit itself, the valence band itself. So they get slight displacement, and they get oriented towards the external applied electric field. Okay, so this displacement is not permanent, it is going to be unstable there. So once you remove the external connection, that is going to, they will come back, that is the valence electron, they will come back to their positions, and this is how we call, actually that is a storage of energy. That movement, that is actually, it is stored in terms of changing the potential energy. Fine. Anyway, so working wise, you can see that is whatever number amount of positive charge developed on the metallic plate, equal amount of negative charge will be developed on the other terminal of the capacitor. That means on the p-type substrate here. Okay. Okay, so this is one phenomena, that is called induced voltage, right? The capacitor that is on the other plate, that is on this region, p-type substrate region, that is induce a negative charge. That is the first phenomena. Second phenomena, that is easier to understand, that is what happens actually as we are connecting p-type terminal to the gate terminal, and S is actually the substrate. Okay. So what happens, the holes which, because p-type material, that is have majority carriers as holes. Holes are the majority carriers, as well there are going to be ions, because there is always an excess of one electron. So they get all the ions, that is atoms, they are negatively charged ions. Okay, so the p-type material has holes as well, negatively charged ions. Okay, now as because of the external battery connection, the holes, they get drifted towards the negative terminal of the battery. So that means they go away from this you can say it is junction, that is this actually I'm not saying it's junction, that is from the metallic con, that is SiO2 layer, they try to go away from this. Okay, so what happens in this region, there is left only negatively charged ions. Okay, so these are the two phenomena. One is, that is a, because of the capacitive construction, there is an induced negative charge in this region, and second is because of holes getting drifted towards the negative terminal of the battery, there is going to be created negatively charged ions in this region. Okay, so overall this region, you can say that is negatively charged, and this is where we can say that n channel is formed. Okay, so this is how there is chain developed an N channel. Okay, with that N channel, there is also a no space, no charge region developed, which is like this. Okay, but this is an N channel region. Okay, that means now electrons can easily flow through this. Okay, and now what is the effect if we increase VGG? That is, if we increase VGG, that is gate is made more positive. VGS is increased, gate is made more positive. What will happen? if gate is made more positive, that means more positive voltage here, that means more negative voltage on the other side, also more drifting. So overall, more number of majority electrons from source to the drain that can move. Okay, so that is more the electrons. Okay, so as VGS is more positive, there will be more current ID, drain current. Okay, similarly, we know that as VDS is more, that is drain voltage is higher than the source voltage, more and more current will be, that is more and more that is electrons will be able to drift towards the source, from the source to the drain. So they will constitute drain current. So as VDS increases, current ID increases. As VGS increases, current ID increases. Okay, so say the formation of N-type channel from the P-type substrate is called the inversion process. Okay, once again understand, that is there was only P type of material, but once you give VGS, once we give VGS, and that is gate is made positive, with that negative, this phenomena start, that is negative charged, that region that gets negatively charged, and N type of it P type region that is now converted into N type region. That means you can say this is the inversion process. That layer which is formed, that is called inversion layer. And now because the N channel is actually enhanced here, it was not previously, it was just enhanced once the external biasing was given. This type of MOSFETs, they are called enhancement MOSFET. Okay, one more phenomena, that is with, as I said, that is as VGS increases, that is as VGS increases, what happens, that is ID current that has to increase. Similarly, as VDS increases, ID increases. But there is one more phenomena, that is when there is VGS, as VGS is also positive, when its gate is more positive, and the when drain is made positive, what happens? See, because drain is more positive, that space, that is the channel that is get bulging towards the drain, that is its width, that will be more towards the drain region compared to near the source region, or maybe in the central region. Okay, so this is how, that is a bulging of the, that is you can say that is bulging, the channel is like this. Okay, channel is formed like this between two N plus regions. Okay, so that is thing. We have not seen till what is the symbol of N channel in MOSFET. So this is one symbol where there are four particular terminals have been shown, that is a source, drain, gate, and the, this is the base terminal or the SS terminal. Okay, it is N channel, you know, that is in N channel the substrate should be of P type, so arrow that goes in this way. Okay, this broken lines that shows it is actually enhanced, and that is actually the channel is actually enhanced and it is not actually there, so that's why there is a broken line. Okay, another symbol for this E-MOSFET, N-channel E-MOSFET, that is like the previous case, but now in this case that is shown here the capacitive construction. This is in general. In case of MOSFET, we will show that is this is a capacitive construction. Okay, and it is N channel. That means, see, there is the arrow is from P to N, right? P to N. So that shows P to N. So that's why this indicates N channel. So this is the source and this is the drain. This is how the symbol for N channel. Similarly, these are the symbol for P channel enhancement mode, enhancement MOSFET, where you can see one way, that is to have four different terminals. The base for P channel is negative, so the arrow that goes towards the base. Okay, similarly, and the E-MOSFET, that is other symbol, that is here, that is not written here, that is source here. Okay, that is gate here, and this is drain here. Drain here. Okay, and because it is P channel, P channel, that means the source is made up of P plus. Okay, that's why the arrow is outgoing from the source. Okay, so these are the symbols. Let us see now based on VGS and VDS the characteristic. So this is the output characteristic and output drain characteristic of E-MOSFET, and this is the transfer characteristic of the MOSFET. Let us see first this output drain characteristic. As we said, that is, as VDS increases in this direction, ID that should increase. As VDS increases, drain increases, that is, drain is becoming more and more positive, ID increases. So like this, but one particular voltage level, that is as was IDSS, that is saturation level, that is going to be almost, that is constant current. There is no more now electrons can be passed through it. So this is a common characteristic. And again, as VGS is increasing, that is as gate is made more positive, that is you can see here, that is gate is more positive as you go on upward side. So as the gate is becoming more and more positive, okay, the ID current that increases, okay, but the gap, consecutive gap, that reduces. Okay, so that effect you can see here, that is, you can see for the smaller voltages of gate, okay, this is gate to ID, smaller voltage of gate, there is less, suppose here 4 to 8 volt, right? If you go from 4 volt to 8 volt, the change in ID is this much, but when you go from 8 to 12, 8 to 12, okay, the change in ID is this much. Okay, as you go here, that is as a constant VDS voltage, this is how you can find, that is as a constant VDS voltage, what is the ID current. Okay, so that drain current has been shown here as a constant VDS, what is the ID current. So that goes here. Here the important thing is this thing, that is the definition of a gate to source threshold voltage level. This is the gate to source threshold voltage level. Okay, so this is, you can say, once the gate is made beyond this threshold voltage, the currents is almost increasing. Okay, and before that threshold voltage, the current level was very small. So this is the transfer characteristic of E-MOSFET. Okay, so if you compare this characteristic with JFET, almost they have the similar characteristic. Okay, the description was not exactly same, but the requirement, that is overall characteristic, they are same. That is here also we can have the amplification possible in the same way, because these are, but now as we know for FATs these are different VGS, and for this VGS, but only thing is now the amplification will not be linear compared to BJT. This is amplification will be non-linear. That is, suppose you can see, if you go from VGS 2 volt to 3 volt, okay, the change in IG, that is ID is this much. Okay, suppose ID, change in ID is this much, but when you go from 1 to 2, between this region, the change in ID is more. So if you have an input voltage VGS that is changing by 1 volt on this side and 1 volt on this side, for the positive half cycle there will be less amplification, for the negative half there will be more. So overall, that is, this is common for a FAT devices, they are actually non-linear amplifiers. Okay, slightly non-linearity is there. Anyway, but the advantage of MOSFET here, that is, as we seen the symbol, that is input, that is on the base side, that is a capacitive construction, and that capacitive, that is silicon oxide layer, that offers very high input impedance. That very high input impedance, that is as far the major requirement when you are having the multi-stage amplifier or any multi-stage devices or multi-stage components. Okay, so when you are having one circuit followed by the other circuit followed by the third circuit, you want that the circuits, they work as if they are independent, they as if they have a definite task and they are working as it is. For that we had seen the requirement was that the input impedance should be high and the output impedance should be low. So the MOSFET, they do have very high input impedance, because the input that is having a capacitive arrangement, the insulator, very thin layer of insulator, that offers very high input impedance. Okay, So this is all about enhancement type of MOSFET. Next we will see depletion type of MOSFET. Thank you.